Forget everything you've been told about military aviation. Right now, there could be a machine in the sky capable of wiping an entire continent off the face of the Earth. And the craziest part is, its true capabilities are still being hidden from prying eyes. Our hero today is the Tu-160 White Swan. Why did Soviet engineers intentionally choke the speed of this supersonic monster? What fatal vulnerability does its unique design conceal? It is affectionately called a bird, but in reality, it is the greatest nuclear predator in human history. Watch this video to the end, and I will reveal the secrets of the legendary Tu-160 that have been kept hidden for decades. The way pilots actually handle this steel Leviathan will simply shatter your perceptions. Ready for the exclusive? Then let's begin. The year is 1968. The Cold War is in full swing. Two superpowers are staring each other down across the ocean, and both perfectly understand that the next great confrontation will not take place on the ground, but in the sky. The United States is working on a new strategic bomber. The program is called the B-1, an aircraft meant to fly fast, far, and high. An aircraft conceived as a universal answer to any challenge. In the Soviet Union, they know about this program and realize they need an answer of their own. But here is the problem. At that moment, the Soviet Union did not have a single intercontinental supersonic bomber. None. They had nuclear weapons, they had ballistic missiles, but they didn't have an aircraft that could cross the ocean at supersonic speed, complete a mission, and return. This had to be fixed. In 1968, Soviet engineers were tasked with something that, to put it briefly, was build an aircraft that doesn't exist in nature. It had to fly further than any existing bomber, faster than the enemy could react, and carry a payload so massive that a single board could change the course of any conflict. The task was set, and that's when things got interesting. Several design bureaus began working on it. Tupolev, Myasishchev, Sukhoi, 4 teams of the country's best engineers. 4 different planes, still on paper. And not one of them initially met all the requirements simultaneously. Imagine having to build a truck that drives at the speed of a race car, carries as much as a freight train, and consumes fuel like a compact car. That was the scale of the contradictions facing the engineers. High speed requires one wing shape, sharp, swept, almost needle-like. Long range requires another. Huge payload requires a third. Combining all of this in one machine was a nearly impossible task. Nearly. Because that was the moment an idea emerged that changed everything. The idea was simple to the point of audacity. What if the wing didn't have to have one single shape? What if it could change its form right in flight, depending on what the plane needed at that very second? You take off, the wings are in one position. You go supersonic, they are in another. You save fuel at cruising speed, they are in a third. The idea of variable sweep wings already existed. The Americans experimented with it on fighters. But applying it to an aircraft of such incredible size, no one had done that anywhere in the world. This solution became the foundation of the winning project, the Tupolev Design Bureau's project. But there is a huge chasm between an idea on paper and a real plane in the sky. To cross it, engineers had to solve the question everything starts with and everything rests on. How do you force a giant wing to move smoothly, precisely, reliably, at speeds twice the speed of sound? Let's forget about planes for a second and talk about birds. Look at how a falcon flies. When it soars, its wings are widely spread, every feather working. But the moment it tucks its wings and dives, everything changes. The body becomes an arrow. The wings press against the sides. And nothing in nature can stop that strike. Nature solved this problem millions of years ago. One wing, 2 forms. For speed and for flight. Soviet engineers wanted to do the same, only out of metal, and weighing 275 tons. The idea of variable sweep geometry is not a Soviet invention. The Americans used it on the F-111 fighter in the 60s. But a fighter and a heavy bomber are like a bicycle and a freight train. The scale is different. The loads are different. The requirements are different. The task was to create a wing that, in one position, allows the plane to take off from a normal runway and cruise economically over long distances, and in another, allows it to accelerate to twice the speed of sound. And all this in a construction that would withstand monstrous loads over thousands of flight hours. How does it work on the Tu-160? The wing is divided into two parts. The inner part is fixed. It is welded into the fuselage and forms a single unit with it. The outer part is movable. This is the part that rotates. Sweep is the angle at which the wing is deflected backward relative to the fuselage. During takeoff and landing, the wing is set at an angle of 20 degrees, almost straight. This provides maximum lift. At high speeds, the wing rotates backward, up to 65 degrees. The plane starts to look like an arrowhead. Air resistance drops. Speed increases. Imagine riding a bicycle and holding your arm perpendicular to the movement. You feel how the wind pulls it back, right? Now, tuck your arm along your body. The resistance almost disappears. Roughly the same thing happens with the Tu-160's wing. The wings are made of high-strength titanium and aluminum alloys. Titanium is an outstanding material. It is lighter than steel but comparable in strength. The problem is that working with titanium is extremely difficult. It is hard to process, capricious when welding, and requires special equipment and huge precision. In the 70s, only a few enterprises in the world could master the production of large titanium structures. Soviet plants managed it. But the most interesting thing is not the wing itself, but what is at the point where it connects to the fuselage. That very element, the hinge assembly. A part roughly the size of a human fist at its core, though the mechanism itself is, of course, much more complex. This is the pivot point. It is through it that all the loads arising in flight are transmitted. Lift, thrust, vibrations, air gusts. All this through one node. Over and over again. Thousands of hours. If this node fails, everything fails. The engineers calculated it with a safety factor that seemed excessive, but practice showed that such a margin was exactly what was needed. Now, about the promise I made a few minutes ago. Why can't the Tu-160 fully retract its wings while on the ground? It's all about the center of gravity. When the wings are extended forward, the plane's center of gravity is in the right place. The landing gear is stable. Everything is balanced. But as soon as you start moving the wings back, the center of gravity shifts. The tail starts to outweigh the nose, and 275 tons of metal risk simply falling backward right on the tarmac. That is why, on the ground, the Tu-160's wings are always in a position close to maximum extension. Only in the air, when the plane is already flying and aerodynamics are in full force, can the wing take any angle. Nature and physics are stubborn things. Even when you are building an aircraft the likes of which the world has never seen, they still dictate their conditions. The fixed part of the wing, merged with the fuselage, gave the designers another unexpected bonus. Inside this space are huge fuel tanks. No extra joints, no weak spots. The body's strength increased. Weight decreased. One solution solved three problems at once. At maximum extension, the Tu-160's wingspan is 55.7 meters. That's about half a football field, from one goal to the center line. And this huge wing rotates smoothly, precisely on the pilot's command. In flight, you barely see it, but it happens, constantly. The wing issue was solved. Now they had to solve the question without which everything else is meaningless. How to make this colossus fly faster than sound. And this is where 4 engines enter the scene, each of which is a miracle of engineering in its own right. There is a simple question that is rarely asked aloud. How do you even lift 275 tons of metal into the air? And not just lift it, but accelerate it to twice the speed of sound? The answer is 4 engines. Kuznetsov NK32 turbofan engines with afterburners. In aviation circles, they are simply called NK32s. Each of them is a separate machine, independent. If one engine stops in flight for any reason, the other 3 continue to work. The plane keeps flying. This isn't just a convenience, it's a fundamental design decision. The engines are located in pairs, two in the left pod under the wing, two in the right. Each pair works in tandem, but each engine remains fully autonomous. Now for the numbers. But first, a small explanation. Engine thrust is measured in kilograms force. This is a conventional measure of how much force an engine exerts to push the plane forward. One Kuznetsov 32 engine in afterburner mode develops a thrust of 25,000 kilograms force. What does this mean in practice? Imagine a cable tied to a plane. The engine pulls this cable with enough force to hold 25 tons of cargo in the air. One engine. There are four. The total thrust of all four engines in afterburner mode is 100,000 kilograms force. That is roughly equal to the thrust of 120 cars working at maximum RPM simultaneously. Only unlike cars, this happens not on the ground, but at an altitude of several thousand meters, at an outside temperature of minus 50 degrees Celsius. But what is an afterburner? Let's break it down simply. A normal jet engine works like this. Air is sucked in from the front, compressed, mixed with fuel, and burned. The hot gases rush out the back and push the plane forward. This is the standard economical mode. Afterburner is when additional fuel is injected into the stream of already burnt gases, right before the exhaust nozzle. It ignites again. Thrust increases sharply. The plane gets a powerful extra boost. The price for this is a sharp increase in fuel consumption. In afterburner mode, the engine consumes fuel several times faster than in normal mode. Therefore, afterburners are not used constantly, but in specific moments when maximum speed or a quick climb is needed. And here is that thing I mentioned. When all four Tu-160 engines engage the afterburner at the same time, it becomes impossible to talk within a radius of several kilometers. At all. The sound is so powerful that people on the ground, even with earplugs, physically feel it as pressure in their chest. This is not a metaphor. This is physics. At the same time, the plane accelerates to 2,200 kilometers per hour. The speed of sound is about 1,235 kilometers per hour. That means the Tu-160 is going about 1.8 times faster than sound. By the time you hear its engines, the plane is long gone. The Kuznetsov 32 engines were the most powerful turbofan engines ever installed on a combat aircraft at the time of their creation. They hold this title to this day. But all this power, 100,000 kilograms of total thrust, afterburners, supersonic speed, is nothing without the person sitting in the cockpit controlling it all. And here arises the question I ask every time I think about this plane. What does it feel like to hold a machine of such dimensions in your hands? Picture this. You are standing next to a Tu-160 on an airfield. You look at it from the bottom up. The landing gear is as tall as a two-story house. The fuselage is wider than a railway carriage. The length of the plane is 54 meters. That is about 18 cars parked bumper to bumper. And somewhere there, in the very nose of this colossus, several meters above the ground, is the cockpit. 4 people. And they are the ones who control everything you see before you. The Tu-160 crew consists of 4 people: the commander, the assistant commander, the navigator, and the navigator operator. Each is responsible for their own area. All 4 are housed in a single pressurized cockpit in the nose of the plane. Pressurized is an important word. At an altitude of 16,000 meters, where the Tu-160 can operate, the outside temperature drops to minus 50 to 60 degrees. The air pressure there is so low that without protective gear, a person would lose consciousness in a few seconds. The cockpit creates its own little world inside, with normal pressure, normal temperature, everything necessary for work. The ejection seats are not ordinary chairs. In an emergency, each seat ejects the pilot from the plane along with a parachute. This is standard practice for combat aviation. But on such a plane, at such speeds and altitudes, the seat must work flawlessly in any condition. Now, about the control sticks, or rather, their absence. On most heavy aircraft, the pilot controls the plane with a yoke, a large wheel similar to a car's steering wheel. It's familiar, understandable, traditional. On the Tu-160, there are no yokes. Instead, there are control sticks, small levers like on fighters. Why? The Tu-160 isn't just a big plane. It's a plane that flies at supersonic speeds. At such speeds, the effort on the control surfaces is enormous. The flight control system works with electro-hydraulic amplification, meaning the pilot gives a command and smart mechanics amplify it and transmit it to the controls. In such a system, a compact control stick is more precise and ergonomic than a large yoke. The commander holds a small stick with his right hand. A movement of a few centimeters and 275 tons of metal smoothly change course. This feeling, according to those who have flown this plane, is like nothing else. One of the pilots described it this way. The first time you sit down, you think, how is this even possible? Such a machine and such a small stick. But then you take it and you realize it obeys immediately. Now, about the detail that few expect to see on board a strategic bomber. The Tu-160 is capable of flying for up to 15 hours without refueling, with mid-air refueling even longer. 15 hours in the air. That's longer than a flight from Moscow to New York and back. 4 people in the cockpit. 15 hours. They need to eat, they need to rest, they need to maintain combat readiness throughout the flight. Therefore, there is a small rest area on board the Tu-160, with folding sleeping bunks, with a place to heat food, with a very ordinary, almost home-like ability to grab a bite and sleep a little while your colleague flies the machine. A bomber with a kitchen and sleeping bunks. It sounds unexpected, but at the distances this plane covers, it is not a luxury. It is a necessity. At an altitude of 16,000 meters, at a speed of 2,000 kilometers per hour, one of the 4 crew members is sometimes just sleeping, because in 3 hours it's their shift, and they must be ready. The cockpit is a separate world inside the machine. Small, functional, thought out to the smallest detail. But before these people first sat in the cockpit of a combat Tu-160, the plane had to go through the most difficult part, the first flight. And what happened in December 1981 on the airfield is still remembered by those who were there. December 18, 1981, Zhukovsky, the Gromov Flight Research Institute, outside Moscow. December, a short day, cold air, gray sky over the airfield. On the concrete runway stands the plane. White, huge. Something like this had never been seen here before. Technical personnel, engineers, designers, everyone who had anything to do with this project gathered on the field. People who had spent years of their lives on this plane, some more than 10 years, some their entire careers. They stand, they watch, and they wait. The journey to this moment took 13 years. 1968, the task was set. Years of calculations, disputes, reworkings, competition of projects, the victory of the variable sweep wing concept. Then, the production of the first experimental prototype. Every detail was made by hand, checked, rechecked. Titanium structures that no one had made in such sizes before. Engines that were assembled one by one. 13 years, and here it stands before you. The crew boards the cockpit. The commander is test pilot Boris Ivanovich Veremey, one of the best test pilots in the country, a man who had taken dozens of new machines into the air in his career, but never one like this. Later, he would say that that morning on the field, there was a special silence. Not anxious, not tense, something else. It happens when people realize that something is about to happen that cannot be undone. Either it flies, or it doesn't. The engines start, one after another. The sound rises. First, a low hum, almost at the edge of audibility, felt more in the chest than the ears. Then, higher, sharper, more powerful. People on the field involuntarily take a step back. The Tu-160 begins to move along the taxiway. Watching it in motion is already a strange sensation. When a machine of such size moves on the ground, it seems to move slowly, almost leisurely, as if it's in no hurry. But then you look at the speedometer and realize that it's an illusion. The plane reaches the runway. A pause. Several seconds of complete stillness. And then, the afterburner. The sound changes instantly. The hum turns into a roar. The roar into something for which it is difficult to find a word. This is no longer sound in the usual sense. This is a wave. A physical wave of pressure that passes through the body. The white plane races along the strip. Faster. Faster. Those standing nearby later said that it was almost impossible to keep track of it with their eyes. Too fast, too unexpected for a machine of such size. And it lifts off the ground. 275 tons of metal head into the December sky. On the ground, silence. A second. 2. Then, applause. Someone takes off their hat. Someone just stands and looks up, not moving. One of the lead engineers of the project, according to witnesses, turned away. He didn't want to be seen in that moment. 13 years, and now it's flying. The first flight lasted about 30 minutes. By the standards of a test program, very modest. No records, no supersonic speed. Just get up, make sure everything is working normally, and come back. Check the main systems. Make sure the landing gear retracts and extends, that the wing changes sweep in flight, that the 4 engines work in coordination. All this for the first time, on a machine that until that moment existed only on paper and in metal on the ground. Boris Ivanovich Veremey landed the plane precisely on the runway, taxied to the parking area. The engines shut down one by one. The silence hit hard. After such a roar, it seemed almost physically tangible. Veremey climbed out of the cockpit. Around him, people. Designers, engineers, technicians. Everyone is waiting. He looked around and said 3 words. The plane is a yes. Nothing more. Just, the plane, it's a yes. In the words of a test pilot of such a level, a man accustomed to evaluating machines with restraint and professionalism, this phrase meant a lot. It became part of the history of the program. But this was only the first step. Ahead lay years of testing. The Tu-160 test program was long and complex. Each system was checked separately, then in conjunction with others, then in extreme conditions, at different altitudes, at different speeds, at different temperatures. The wing changed sweep hundreds of times, and each time engineers analyzed the data. The engines were run in all modes, including afterburner at limit parameters. There were problems. They always happened during the testing of a fundamentally new machine. Something was refined on the fly. Something was redone. Some solutions, which seemed correct on paper, behaved differently in the air, and engineers returned to the blueprints. This is a normal part of the job. That is exactly what tests are for. In 1984, 3 years after the first flight, the Tu-160 was accepted into serial production. Production was launched at the Kazan Aviation Production Association, one of the country's largest aircraft factories. Kazan, huge workshops, specifically expanded to fit a plane of such dimensions. New equipment, specially trained workers, technologies that had not been used in civil or even military aviation on such a scale before. Every serial Tu-160 was assembled by hand. This is not a conveyor in the usual sense. This is artisanal work. Months for one plane. Thousands of people involved in the production of components all over the country. The plane, which for 13 years existed only in the minds of engineers and on drawing boards, began to come out of the factory gates. One board, then another, and each of them received a name. But more on that in a moment. First, about what these planes could do, about the records. 46 of them. Each has its own story. There is an organization that monitors records in aviation. It is called the Fédération Aéronautique Internationale. It is the one that records, verifies, and officially registers everything that happens in world aviation worthy of the title of a record. Speed, altitude, range, payload, climb time, dozens of parameters. Throughout the history of aviation, records have been set by hundreds of aircraft, fighters, civil airliners, experimental machines created specifically to fly faster or higher than everyone else. The Tu-160 set 46 world records. Not a special record-breaking machine created only for achievements. Not a light experimental aircraft without weapons and equipment. A serial heavy bomber, in full combat configuration, with a full crew, set records one after another. Let's break down what exactly this means. Let's start with speed. During test flights, the Tu-160 accelerated to 2,200 kilometers per hour. This was the achieved, recorded speed. Not theoretical, not estimated. Real. On serial planes, it was programmatically limited to 2,000 kilometers per hour. But the machine itself is capable of more, and this was proven. 2,200 kilometers per hour. Let's translate this into understandable images. From Moscow to London, about 2,500 kilometers in a straight line. On a Tu-160 at maximum speed, this takes a little over an hour. 1 hour, and you are at the other end of Europe. Or here is another way to understand this figure. A bullet fired from a standard army pistol flies at a speed of about 350 to 400 meters per second. The Tu-160 at maximum speed is about 610 to 620 meters per second. A white plane 54 meters long flies faster than a pistol bullet. Think about that when you look at its size. Now, altitude. The service ceiling of the Tu-160 is 16,000 meters, 16 kilometers above the ground. At such an altitude, passenger airliners don't fly. Their cruising altitude is usually 10 to 12 kilometers. 16,000 meters is already the border of the stratosphere. There, the air temperature drops to -50 to 60 degrees. The air pressure is 4 times lower than at the Earth's surface. The sky there is no longer blue. It is dark blue, almost black. If you look up from this altitude, you can see stars during the day. At such an altitude, interceptors operate. Specially created light machines whose task is to take off as quickly as possible and climb as high as possible. A heavy bomber weighing 275 tons shouldn't operate there, by all laws of logic. The Tu-160 operates there. Next, range. Without mid-air refueling, the Tu-160 covers a distance of over 13,000 kilometers. With maximum load, about 10,000 kilometers. 13,000 kilometers is the distance from Moscow to Sydney, Australia, almost to the other end of the planet, without a single landing, without refueling. Fuel is a separate story. The Tu-160 takes on board about 170 tons of aviation kerosene. 170 tons is about 6 railway tankers. All this is placed in internal tanks built into the fuselage and wing structure. Now, load. The maximum payload of the Tu-160 is 40 tons. 40 tons is the weight of about 25 ordinary cars. All this inside 2 cargo bays within the fuselage. Nothing is visible from the outside. No external pods. No structures under the wing that would increase air resistance. Everything is inside. This is also a record. Such payload, in combination with such speed and such range, has not been shown by any aircraft in aviation history. And here is the moment I promised to tell you about. One of the 46 records was set during a scheduled test flight. The crew was carrying out a program, checking system operation in a specific mode. Routine work, without record-breaking ambitions. At some point, the navigator paid attention to the readings of the navigation equipment and the flight parameter control system. The numbers didn't match what was expected. He checked again. Then, again. Then he called the commander. It turned out that the plane, performing a scheduled task in routine mode, had incidentally broken the existing world record for one of the climb parameters, just because it was flying the way it knows how, without trying. After landing, the data was handed over to the Fédération Aéronautique Internationale. The record was fixed and entered into the register. The crew, according to one of the participants of that flight, found out about it already on the ground. Over tea. That is what a reserve of characteristics means. But 46 records are not just a set of beautiful numbers in a table. Behind each of them stand concrete people. Crews who took to the air, engineers who prepared the plane, technicians who worked nights before record flights. And each plane that set these records had its own name. Because the Tu-160 is the only strategic bomber in the world where each unit bears its own name. Like a ship, like a living being. Where did this tradition come from, and what is behind it? In military aviation, it is not customary to name planes. They have tail numbers. There are factory indices. There are serial designations. A machine is a machine. A tool. A unit in a registry. The Navy, that's a different story. The tradition of giving names to ships goes back thousands of years. A ship is a living being. It creaks in a storm. It obeys the helm. It can save or fail. Sailors always knew this, and they always gave their vessels names. With the Tu-160, something unusual for aviation happened. Each board received its own name. Like a ship, like a living being. Why? If you look at it from a practical point of view, there are several explanations. The Tu-160 was built one by one. Each plane, months of work by hundreds of people. Each board differs slightly from others. In characteristics, in behavior in the air, in small structural features that inevitably arise during manual assembly. Crews who fly a specific plane for years know it, feel it, bond with it. In such a situation, a name is not sentimentality. It is precision. It is a way to speak about a specific machine as something separate, unique, to distinguish it from others. But there is also another side to this tradition. The names that Tu-160 boards receive are not random words. These are the names of people who had a direct connection to aviation. Pilots, designers, test pilots, people who devoted their lives to the sky, and left something in that sky that doesn't disappear with time. One of the first boards received the name Mikhail Gromov, Mikhail Mikhailovich Gromov, an outstanding Soviet pilot. It is his name that is given to the Flight Research Institute in Zhukovsky, the very place where in December 1981, the Tu-161st lifted off the ground. The circle closed. The first flight over the institute named after him, and the name on the board. Another board bears the name Ilya Muromets. This name is known to everyone in Russian culture. A hero from folk legends. A person who, according to legend, couldn't walk until the age of 33, and then stood up and performed feats that are still remembered to this day. An image of power awakened from rest. It's hard to come up with a more precise metaphor for a plane that stands on the ground as a motionless white colossus, and then heads into the sky at supersonic speed. There is a board with the name Alexander Malachi, Alexander Ignatievich Malachi, a pilot twice awarded the title of Hero of the Soviet Union, a man who, during the years of the country's hardest trials, performed more than 300 combat sorties. His name on the side of a strategic bomber is not just a memory. It is a connection of generations between those who flew then and those who fly now. Vasily Reshetnikov Board. Vasily Vasilyevich Reshetnikov, a pilot, a commander, a man who went through everything and lived to be 98 years old. Until the last years of his life, he was interested in aviation, met with crews, monitored what was happening in the sky. When a plane with his name on the board taxied to the runway, it wasn't an abstract tribute. It was a living connection between a person and a machine. Now, about what I promised. One of the boards bears the name Valentin Bliznyuk. Valentin Ivanovich Bliznyuk, the chief designer of the Tu-160, the man who led the creation of this plane, who knew everything about it, Every detail, every decision, every compromise between what they wanted to do and what physics and technology allowed. His name was given to the plane not after he passed away. He found out about it during his lifetime. Imagine such a moment. A person who spent the best years of his life creating a machine, who saw it on drawing boards even before it existed in metal, who was on the field on December 18, 1981, and watched as it first went into the sky, and who one day comes to the airfield and sees his name on the side of a white plane. Not a rank, not a position, a name. Blizniuk, according to colleagues, was a man of restraint, not prone to public emotion. An engineer to the core, precise, demanding, focused on the task. When asked what he thought about this decision, he was silent. Then he said that this is an advance, that the plane still had to prove it deserved to carry any name. The plane proved it, 46 times. The tradition of naming Tu-160 boards continues. Each name is a choice, conscious, weighty. A name must mean something, must carry a history worth remembering. And here is what's interesting. Crews who fly a specific board for years begin to speak about their plane differently than others. Not board number so-and-so, but by name. This happens involuntarily, gradually. The machine becomes something more than just a machine. One of the crew commanders told an interview how, after a long flight, more than 12 hours in the air, he was approaching to land and caught himself thinking that he was mentally talking to the plane. Not literally, but something like, well, come on, a little more, hold the course. Like experienced horsemen talk to a horse, or to an old ship in a storm. Maybe that is the answer to the question, why planes get names. Not because it's customary, but because the people who spend thousands of hours in the air with these machines begin to feel something alive in them, something deserving a name. The Tu-160 is the largest supersonic plane in the world, the most powerful, the most graceful, if that word is at all appropriate in relation to 275 tons of metal. And each of its units is one of a kind, unique, with its own name. But the history of these planes is not linear. There is a moment in it that is uncomfortable to talk about. A moment when it seemed that the White Swans might disappear altogether. When the program, on which decades and huge human labor were spent, was under threat. And the question was not about records and not about names. The question was simpler. Will this plane fly at all anymore? 1991. The Soviet Union ceased to exist. For most people, this is history, politics, dates in a textbook. But for those who worked in aircraft factories, in design bureaus, at flight bases, this was a concrete moment when the world around them changed within a few months. Funding stopped. Programs were frozen. Factories switched to a reduced operating mode. People left, to where they were paid at least something. The Kazan Aviation Production Association, the factory where the Tu-160 was assembled, was no exception. Production effectively stopped. Workshops that were specifically expanded and refitted for the assembly of the world's largest supersonic plane became empty. Several finished and partially finished boards remained standing in the workshops, without engines, without avionics, without the prospect of ever getting into the air. This was not the end of the program in the official sense. The program was not closed by order. It was simply no longer funded, which, in essence, is the same thing. But the problem was not only at the plant in Kazan. After the collapse of the Soviet Union, some aviation units ended up on the territory of new, independent states. This also applied to the Tu-160. 19 aircraft of this type were based at the Pryluki airfield in Ukraine. 19 boards. Almost half of the entire fleet. Ukraine in the early 90s found itself in a difficult situation. Maintaining, servicing, and operating strategic bombers of this class is a huge expense. Special fuel, specially trained crews, spare parts, infrastructure. The young state didn't have enough of any of this. Some of the planes were eventually dismantled and decommissioned, as part of international agreements on the reduction of strategic offensive arms. The United States allocated funding for this program as part of the so-called Cooperative Threat Reduction. This was a period when former Cold War adversaries were agreeing on mutual reduction of strategic arsenals. American officials were personally present at the decommissioning of some Ukrainian Tu-160s. Photos from those years remain. White planes with cut-off tails, wings removed from fuselages, machines that could fly but would never fly again. These were not old planes. Some of them had very few flight hours, practically new boards. Russia received 8 planes from Ukraine in 1999, not for free, as part of debt repayment. 8 boards. They flew to Russia under their own power. Crews ferried them to Russian bases. When these planes landed at Russian airfields, technicians and engineers who met them later said that the state of the machines varied. Some were in good condition. Others required serious technical maintenance after several years of limited operation. But the main thing, they arrived, under their own power. They still knew how to fly. Meanwhile, in Russia, the situation slowly, very slowly, began to change. In the late 90s and early 2000s, funding for aviation programs began to recover. Not immediately, not in full, but the process started. In 2008, the last Tu-160, assembled according to the Soviet project with almost no changes, left the Kazan factory. Formally, production continued all this time, but at a very slow pace, with large breaks, finishing what was laid down in the Soviet period. And then the question arose that sooner or later faces any complex technical system. The plane was created in the 70s and 80s. Electronics of that time is one generation. Capabilities of that time, different. The world has changed. Technology has gone far ahead. What to do with a plane that is still physically flying, but carries stuffing 40 years old? The answer is modernization. Deep. Fundamental. This is how the Tu-160M project was born. The letter M stands for modernized. But the scale of the changes is such that this word barely conveys the essence of what is happening. In 2015, an official decision was made to resume serial production of the Tu-160 in a modernized version. The Kazan plant again began preparing for the production of the world's largest supersonic bomber. Almost 30 years after that production effectively stopped. What changed in the Tu-160M? Let's start with the engines. The original Kuznetsov NK-32 is an outstanding machine. But by the time the development of the modernized version began, production of these engines had long since ceased. The technological chain was partially lost. Tooling, de-equipped. Engineers were faced with a task that, without exaggeration, can be called recreating the technology from scratch. The new version of the engine received the designation Kuznetsov NK-32 Series 02. Externally, it looks like the original. In essence, it is a new machine. New materials, new production methods, improved fuel efficiency, increased resource. Designing and recreating the production took years. It required finding or educating specialists again who knew how to work with such engines. Part of the technical documentation was restored from surviving samples, literally from existing parts, which were disassembled, measured, and described anew. And here, about what I said at the very beginning of the conversation about modernization. While working with the Design Bureau's archives, engineers discovered technical documentation dated from the mid-70s. A solution to one of the problems with engine component cooling. A solution that designers then developed theoretically, calculated, and documented. But they didn't launch it into production. They ran out of time. They were working on the first prototype. Deadlines were pressing, and the solution was postponed. For later. Later stretched for half a century. Engineers of the 21st century took this documentation, verified the calculations using modern modeling methods that simply did not exist in the 70s. The calculations were confirmed. The solution was correct then. It remains correct now. and it was implemented in the Kuznetsov NK-32 Series 02 engine. An idea born in the 70s of the last century flies in the sky today. Think about that. The avionics of the Tu-160M is a separate story. The original instrument panels, analog indicators, navigation and control systems of the 80s were replaced by digital complexes. New displays, new navigation systems, including those using satellite systems that didn't exist at all at the time the original plane was created. New means of communication, new control systems. The cockpit of the Tu-160M and the cockpit of the original Tu-160 are like the cockpit of a modern airliner and a cockpit of a 40-year-old plane. The same layout, the same 4 seats, but inside, a different world. At the same time, the plane's airframe, fuselage, variable sweep wing, landing gear, overall layout are preserved, because there is no point in changing them. They were correct in 1981. They remain correct now. Physics hasn't changed. On January 25, 2022, the first newly built Tu-160M took off from the runway of the Kazan plant. Not a modernized old board, a new plane, built from scratch to an updated project. On the airfield that day, people gathered again. Engineers, designers, technical personnel. Like in December 1981, only other people. Another generation. The plane lifted off the runway and headed into the sky. Those who stood on the field and looked up later said the feeling was similar. The same silence a second before the wheels lift off the ground. The same wave of sound. And the same feeling that something is happening now that cannot be undone. 40 years separate these two moments. 2 takeoffs. 1 machine. The White Swan has returned. Let's pause for a second. We've come a long way. From the offices of 1968, where engineers received a task that seemed impossible, through drawing boards and titanium structures, through a December morning in 1981, when the ground shook and the white machine first went into the sky, through 46 records, through names on the boards, through empty workshops of the 90s, and through a new takeoff in 2022. This is a long story, but I want to ask you one question before we finish. What is this story really about? You can say, it's a story about a plane, about technical solutions, about numbers and records. And that will be true, but not the whole truth. Because the Tu-160 is not just a plane. It's an answer to a question that people have asked themselves since they started building anything at all. How far can you go if you don't stop? Think about this from this angle. In 1968, when the design of this machine began, there were no computers in the sense we understand that word today. Everything the engineers did, calculations of loads on titanium nodes, aerodynamics of variable wings, thermal regimes of afterburners, all this was calculated by hand, on paper, with slide rules, with arithmometers, by teams of people who distributed parts of huge equations among themselves and brought the results together. A modern engineer with a laptop can simulate in a few hours what used to take months of work by whole departments. But these people, without laptops, without programs, without the ability to press a button and get a ready answer, created a machine that still has no analogs in the world. Think about this. For real. The largest supersonic plane in aviation history was designed by people with pencils and slide rules. What does this say about the human mind? About the ability to solve tasks that seem impossible? I don't know the exhaustive answer. But every time I think about it, I get something like admiration. Not for the machine, for the people who created it. Let's go back to the beginning, to the image everything started with. Airfield, early morning, mist over the concrete. The silence is so dense you can hear metal creaking in the wind somewhere far away. And then, the sound. A low, almost infrasonic hum that starts somewhere deep in the chest before it reaches the ears. 4 Kuznetsov engines reach operating mode one after another. The hum becomes a roar. The roar becomes a wave. The wave presses on everything around, people, buildings, the ground itself. And out of the mist, it appears. White, huge, implausibly large to fly. Wings, 55.5 meters in span, are spread out in cruising position. Nose, long, pointed, looks straight ahead. No extra corners, no accidental lines. Every curve of the body is the result of thousands of hours of calculations and wind tunnel testing. A beautiful plane. Truly beautiful. Not decoratively, but with the beauty that arises when form fully corresponds to function. When nothing can be taken away and nothing can be added. When every line is justified by physics and mathematics. A swan. Not an accidental nickname. Look at a swan in the water. It's huge, heavy. From the ground, you won't immediately believe that such a bird can fly. But it flies. And in flight, it is one of the most beautiful sights that nature can offer. Strength and grace at the same time. Power and precision in one movement. The Tu-160 was called the White Swan, not by order and not by regulation. This name was given to it by people who saw it, who stood next to it on the airfield and watched it accelerate and head into the sky. Names that live are those that are born themselves, without official decisions, just because you can't say it any more precisely. But back to the question I asked at the beginning of this section. What is this story really about? I think it's a story about the fact that between the impossible and the possible is not a chasm. There is distance. You can cross it. Not immediately, not without difficulties. Sometimes stopping and returning. Sometimes finding in the archives a solution that was waiting for its hour for half a century. But you can cross it. In 1968, the task seemed impossible. An intercontinental supersonic bomber with variable sweep wing, capable of carrying 40 tons of payload and covering a distance from Moscow almost to Australia without landing. Such a plane didn't exist anywhere in the world. 13 years later, it took off. This is a story not only about engineers and not only about one specific plane. This is a story about what happens when people decide not to stop at a task just because it's complex. When they take a pencil or a slide rule or a modern computer, it doesn't matter, and begin to calculate, again and again, until the numbers add up into a plane. And then the plane will fly. There is one more thing I want to say before we finish. The Tu-160 now is not a museum exhibit, not a memory of the past. It flies. Right now, as you watch this video, somewhere over Russia, over the Arctic, over the ocean, perhaps a routine flight of one of the White Swans is taking place. A crew of 4, cruising altitude, engines in operating mode. Autopilot leads the machine along the route. One of the pilots, maybe, is now drinking tea in that very small kitchen that wasn't supposed to surprise anyone on board a strategic bomber, but surprises to this day. Another looks at the navigation displays, those very digital ones that appeared in the Tu-160M instead of the analog instruments of the 80s. And outside the board, minus 56 degrees. The pressure is 4 times lower than Earth's. The sky is so dark that stars are visible. 16 kilometers above the ground, 2,000 kilometers per hour. A white swan in its element. Do you know what strikes me most in this story? Not records, not numbers, not sizes, but this. The people who created this plane created it for others. For those 4 people in the cockpit. For those who will fly this machine years and decades after the designers themselves have left. The engineer who in 1970 came up with the solution for engine node cooling and wrote it down in an archive folder didn't know that his idea would fly in the sky in the 21st century. He was just solving a task. Accurately, honestly, to the end. That also says something about people. The Tu-160 is not just a plane. It's 54 meters of human persistence, 275 tons of refusal to stop, 46 records of what happens when a task seems impossible, but is solved anyway. A white swan. It took off in December of '81. It flies today. And as long as its white silhouette passes in the sky above you, the story continues.